Now I'm going to invite Saurabh to take over and present Ablation Cam. So, Saurabh, all yours. You can share your screen and my screen will go away.
Okay. Are you able to hear me?
Yes.
Yes.
Are you able to see my screen?
Yes.
Yeah.
Oh, yeah, great. So hi, everyone. My name is Saurabh, and I'm going to explain the Ablation Cam. Yeah. Okay. So, so this Ablation Cam is basically my work in collaboration with Dr. Harish Ramaswamy during my time at RBCDSAI as a project associate. I know like most of the people like are new to AI or interpretability. So I'll try to keep the talk as much as accessible to the larger audience, and at the same time try to go into depth into certain things. But every time if I reference a topic, I'll also take into consideration for the people who don't know things like Jacobian metrics and all those things, and give a high level idea of what I'm trying to say. So with that, I'll just start. I'm not able to. Okay. I didn't know like Professor Harish had already some slides on convolutional neural networks. So just bear with me. So convolutional neural networks are very similar to fully connected neural networks, and the only difference here is that we have filters which convolve over the channels of the preceding layer. CNNs are found to work very well for image datasets, and they work well because they are able to retain the spatial information. For those of you who don't know, visual explanations help us understand how did a network arrive at a particular output while highlighting regions in an image that were most influential to its decision. For instance, if this image is classified as dog by the network, the corresponding explanation will look something like the image on the right-hand side, where the visualization highlights area near the face of the dog. So basically the output of a product that is Ablation Cam will look something like this. So or any visualization technique will highlight the portion of the body of the category. So here we have plotted visual explanation for dogs. So it's just highlighting the face of the dog. And many of you might think like, okay, when we see a dog, we consider is a complete global structure. Like for us, the dog is not just the face, it's like the entire body, its tail and legs and all the stuff. So you just need to know that convolutional neural networks are discriminative models. And what that means is they are basically closed set, and for them, the entire world is just the categories on which we train them on. So basically, they just try to understand each category as how it differs from the other categories. So here, the model most probably learned how a dog looked by discriminating or discerning it with respect to other categories like cat and frog, etc. So in ImageNet data set, like there are around like 1,000 categories. So it is 1 versus rest, like 1 versus 999 categories. Okay. So quite a few efforts have been made in the recent past to generate good explanations, and the vast majority of this work has relied on back-propagated gradients. So in this work, we identify how crucial, there are some crucial shortcomings of this family of approaches and propose a simple gradient-free alternative. So people who don't know what are back-propagated gradients is, so back-propagation is a technique which is used to train neural networks or convolutional neural networks. And in this technique, we basically use the gradients. So the gradients are used to train the weights. And so most of these techniques use the same gradients to generate the explanations. And if you are aware of interpretability, then you must be familiar with all these papers, and this picture might also look familiar to you. Okay, so now I'll just go through a quick overview of what are the weaknesses with the existing gradient-based techniques. And these are the weaknesses of most of the gradient-based techniques. And later I'm just going to contrast our technique with a particular technique called Grad-CAM. Grad-CAM was the state-of-the-art technique used for generating visualizations. So gradient-based methods suffer from the problem of gradient saturation. On the account of this, it fails to produce reasonable visualizations for very high confidence decisions. As you can see on the top, if an image is predicted with 42% confidence, gradient-based technique give good visualization. On the other hand, if there is another image which is predicted with very high confidence, like 99.99%, these same techniques fail abruptly to provide any good visualization. The second weakness is the loss of spatial information, and we found that the gradients do not retain spatial information of activations. Suppose we make a forward pass of an image through a CNN and observe any feature map of final convolutional layer by resizing and overlapping it with the original image. So I'm just going to show how it can be done. It's like, so here we have this image is just forward passed to the convolutional neural networks, and we get the probability of various categories being recognized, and among them the dog category is recognized with the highest probability. And suppose we select this particular feature map and just try to visualize it. When we say we are trying to visualize a particular feature map, what we try to do is just take those activations and overlap with the original image and then view it as a heat map. So, and then if we try to observe its corresponding Jacobian metrics, we see that the gradients lose the spatial information of the feature map. But still, this same metrics plays a central role in many existing gradient-based techniques to provide spatial explanations. Hence, we've thought that there is a need for a gradient-free alternative. If people are not able to understand what is Jacobian gradient metrics, or what I'm trying to say here is basically, so this was the node, this was the category which was predicted. And with respect to this category, we just took the gradients of these individual activations. And after that, just same like here, we just try to overlap with the original image. And we expected that, like since there was some spatial context over here, the back propagated gradients will also preserve that context. And the part of the reason that this context is not being preserved is because here we have the convolutional layers, which are able to restore the spatial information. Whereas if we go further, we have this fully connected layer. And they just are not designed to maintain this spatial information. And so that's why, like, we thought like we can improve over the existing gradient-based techniques. So feature maps are known to act as concept detectors. And for example, suppose this feature map, there is a feature map which detects a lamp in a given image and maybe assisting the network to recognize an image or a scene to be that of a bedroom. Intuitively, if the lamps were of any significance to bedrooms, erasing them would cause a drop in the class score. This can be easily achieved by setting the activation values of this feature map to 0, so that the further layers no longer view lamps, and we just build upon this observation to build our technique. So this was the overview, like what are we thinking, or what was the line of thinking before we were trying to build this technique. I'll just show schematically. So this is an image and it's been recognized as that of a bedroom. And suppose this particular feature map, just select this feature map, and we see that it just activates, or it has a very high values for lamps. So if once it detects lamps in an image, it activates very highly. Suppose we just set the activation values to 0, that is just disable these activations. Then what essentially we are doing is just ablating this particular lamps and just then making a forward pass. And if the lamps are relevant to, recognizing a scene as that of an bedroom, then we'll see that there is a drop in the probability score. So now I'm going to talk about our technique, but before doing that, I'll just take some questions. Okay, fine. So there are no questions, or I'm not able to see them.
No, there are no questions.
Oh, okay. So basically, so I'll just explain what our approach is like. So in our approach, we first do a forward pass of the image to the network to get the class score. Let's call it YC. And then we, to measure the importance of this kth feature map with respect to a class node, we just ablate it and pass it to the rest of the network. We thus get to observe the drop in this score in absence of the concept represented by the feature map. And if the concept was relevant to the class, this drop will be significantly high. So that is the core of our idea. So basically, this is how we thought like we could associate importance to each feature map and then get a visualization. Basically, we just select any kth feature map, just do an ablation of it, and then further forward pass it to the rest of the network and see the class drop in the class score. And the importance or the weight for each feature map will just be the drop in the class score due to its ablation. So here we see the weight associated with the feature map number 1. We use these weights to carry out a weighted linear combination of feature maps to produce the heat map as shown here. So here we just multiply the weights with the activations of the feature maps, and then we just sum them up. And then we get basically a heat map visualization. And you can see here the red values are the higher values, the values which are higher in importance, and thus they have higher values, higher numerical values. Then we take this particular heat map and overlap with the original image and produce the Ablation Cam Visualization. And here is one qualitative result comparing Ablation Cam Visualization with respect to Grad-CAM. And the image class is person. So the network is able to, so we see that a network was able to recognize that this image contained a category called person, but the Grad-CAM visualizations were not that faithful. So when we say faithful, it means that it was not very consistent with the model, whereas the Ablation Cam was able to detect the face and hand of the person. So here are some more examples, and you can see even more examples in my paper, especially in the supplementary material. Okay, so I think like someone asked in the chat, like, is there a metric to just measure how one particular, how good is a visualization technique, or how can we compare two visualization techniques and that to objectively and say like, okay, this particular technique is better than other. So let me give you some intuition of what we are trying to measure here. Good visualization explanation will highlight the most salient regions. If we only feed this region pixels to the network instead of the entire image, the drop in the class activation score should be minimum. So lower the drop in the score, the better is the technique. So here we have an image of a leopard. And this is the visual explanation. And this can be by any technique, Grad-CAM or Ablation Cam. And further, we only retain the top X% of the most significant pixel highlighted by the visualization technique. So here you can see like these are the spots on its body, and these are highlighted as red. So it took some like top 50% of the pixels in the image, which were considered as most salient by the technique. Now to calculate the insertion metric, we make a forward pass of the image to the network and get a class score of the leopard. Then we pass only the selected pixels and analyze the drop in score. So here we make a first forward pass and check what is the score for leopard, that's YC. Then we just take the top X% pixels and again make a forward pass and check what is the drop in the score. And the insertion metric is just percentage drop in the activation score. And here is like a graph which shows like how on an average our technique compares with other techniques. So this is, we are comparing our technique with Grad-CAM and Grad-CAM++. This is average drop in class score for ImageNet validation data set using VGG16 network. Here we retain only 50% of the pixels of the original image. And also we like to demonstrate that besides like, so in our paper, what we tried to do was just besides showing that our technique is better than other technique on this particular metric, we also showed like there are some really good properties that visualization technique should possess, and how Ablation Cam performs on them. So before going ahead, I'll just take some questions about any questions about my technique that you might be having. So what about accuracy? So I don't think like that was a question for me. Okay. Could you please re-emphasize the difference between grad and ablation? Oh, okay, fine. So grad and ablation, basically, it's difficult to explain. Like, what I'll do is just go to the slides. Here. So, okay, basically what Grad-CAM does is like, it takes this, the gradients with respect to the output node. And then what they do is just use this gradient matrix. Then they take an average of the gradient matrix to calculate the weight associated with each feature map. On the other hand, Ablation Cam, what Ablation Cam does is it will just ablate this particular feature map and then check how much is the drop in the class node. And that particular drop we use as a weight. And the advantage is that we don't suffer from the problem of gradient saturation. Okay. If we have multi-level, multi-class image data set, how does Ablation Grad-CAM technique help to visualize? I'm not so sure what you are trying to ask. Like, what do you mean by multi-level, multi-class image data set? This is question by Abhishek. Okay, fine. I'll just move on to the next question. So, how do you systematically identify which weight map to look at? Oh no, we just look at all weight maps. So if it was not clear from my explanation, like we don't know like what exactly each feature map represents, as Professor Harish already told. Like if we just try to visualize the feature maps, the concept that we see are like very vague and they are not very realistic. So what we try to do is just try to see which particular feature maps are important for a particular class and which are not, and then just do a weighted linear combination of those. What are the limitations of Ablation? And I'll get to that in further slides. So if there are any more questions related to Ablation Cam? Is ablation technique similar to influence functions? Can you just briefly explain what you mean by influence functions here? Okay, I'm not so sure like what you meant by that. Wherein you remove certain, yeah. Okay, yeah, certain input features, yeah. So it is basically very similar to that. If you are referring to any particular paper, like then I can explain how it differs from that. Explain the signification. That can be different from activation. Okay. Okay, fine. So basically, Karthik is excellent. Can you explain the significance of Grad-CAM having a Jacobian matrix that doesn't preserve spatial info? And how is the gradient map different from activation map? So gradient map is different from activation map simply because we don't use the gradients. We just do ablation, like just set the activation values to 0 and just see how much is the drop. And explain the significance. So the significance of Jacobian matrix. So why it doesn't preserve spatial information is because of fully connected layers. And you might argue like there are nowadays the most of the convolutional neural networks don't use fully connected layers, but there are many applications which I will discuss later, like visual question answering, image captioning, where you have to use a fully connected layers in for RNNs or something like that, and where using a Jacobian matrix can really hurt interpretability and a major impact on output. Okay. Sensitive to orientation and scale of object of interest. It is so when we say it is sensitive to orientation and scale of object of interest, so I'm assuming that you mean like if the orientation will change, then it will give a different interpretation. So it depends on it basically depends on the network. If the network is overfitting, definitely so basically it is very faithful to the network. So whatever network thinks is a reason why this particular image should be categorized as this particular category, then it will just highlight that particular part of the image. So if the network is overfitting, I'll show you one example later. If the network is overfitting, and then you can really identify that. And so if the network is overfitting, definitely the network will be sensitive to orientation and scale. In that case, the interpretations will also be sensitive to those. Can we substitute epsilon with instead of 0 instead of complete block, we temper it down? Yeah, you can do that. So basically, when we published this paper, the one thing I was not able to do was like instead of just ablating, I could have used something, some other value, and many of the papers suggest this value. So just you have to just most of the papers just try to get a average over all the values of that feature map and just take that average value as the baseline instead of 0. But no, that won't make much of a difference here, but you can certainly do that. More than one class that contains a large number of different objects. How does Ablation Cam technique help to visualize? Yeah, so these are really good questions. Like how, if there are two categories in single image, how does Ablation Cam technique help to visualize? I'll show like if there are multiple instances of the same category in an image, the Ablation Cam works better than Grad-CAM. At the same time, if there are two different categories in the same image, then we can plot the Ablation Cam with respect to each of these categories, that is each of these class nodes, and still get good visualization. So that is a concept called class selectivity. Did you visualize how does Ablation Cam work on two different class objects in the same image if your model is 10 and if it passed test image where both exist? Yeah, Abhishek, I did that. I'll just show an example for the slides. everyone. Oh, thanks. Okay, fine. Any more first? So does this technique fall under the attribution map paradigm? Yeah, to some extent it does fall under the attribution map paradigm. And but it is not similar to any work done previously. If you are referring to Sundarajan's paper of integrated gradients or something like that, it has some subtle differences. Okay, okay, I'll just continue. All right. Where was I? So now I'll just show what are the desirable properties of a visualization technique. And here we see like how we can use a visualization technique for model selection and also to identify if there is any bias in the data set. So we usually use accuracy as a measure of performance of any model, but do we really care what these models have really learned? An accurate model might as well as be overfitting to the noise, which is present in training as well as test set. We illustrate this with a simple example. We take two models, LXNet and VJ16, trained on the same ImageNet dataset. We already know that LXNet has a higher error rate than VJ16, and hence we would expect it to not generalize very well. So here we have LXNet with 43.45 top 1% error, and VJ16 is 28.41. And as we see, the Ablation Cam does confirm our hypothesis. So we take an image of a bird, which is predicted accurately by both the models with sufficiently high confidence. And then we can see here that visualization shows that LXNet is overfitting to the background, whereas the VG16 is paying attention to the body of the bird. So imagine if you can do this for models with nearly same test accuracy and select the better one. And also if we can just identify if there is a bias in a data set. So one example of bias in data sets or overfitting of the model, which I can give is like I was looking at a visualization and it was of Siberian Husky, and Siberian Huskies are mostly found only in cold regions. So most of the images had snow around them. And and the accuracy of the model on Siberian Husky category was around like 95% or something. But when we visualize now why this particular model is predicting an image to be that of a snow, or that is of a Siberian Husky, we see that the model was overfitting to the background. It was highlighting the snow area in the background. And that is not ideal, right? So if we just feed it snow, as an image of just as ice or snow, it will just predict it as Siberian Husky. So there we could see like how there is a problem of overfitting, or even we can see sometimes like there are some biases in the data sets, biases towards gender or race, and this can be eliminated using Ablation Cam. Someone asked me how does it perform to detect multiple occurrences of the same category. So I wouldn't say like a Grad-CAM doesn't detect multiple categories at all, but the issue with gradients is like they need to be scaled again. So there is a lot of what you can say the scaling issue, and what happens is it only highlights a particular portion with very high intensity, and it tends to neglect the rest of the parts. And so on the other hand, Ablation Cam does a better job of detecting multiple categories of multiple occurrences of the same category in the image. So Ablation Cam visualizations are robust to adversary images. So people who don't know what are adversary images, they are basically when you make very small changes to the original image and the network gives a completely different output. And these changes are not even visible to human beings, not to the human eye. So in original image, we have a boxer dog category predicted with 42% confidence by the network. This probability reduces to 0.02% for adversary image, but the visualization with respect to this class node remains almost the same. And you might be wondering, like, why is this useful? Like, there has been growing interest in how these visual explanations can be used to defend against adversary attacks. So right now there is a colleague who is working on these things, and they're just trying to create a decision trees out of the visual explanations and try to see if they can be used to defend against the adversary attacks. Next thing, I'll just like to show the what you can say, the application of Ablation Cam to more complex tasks. So we see here one example of image captioning. So here the image generated is dog is running across the beach, and if we see the visualization with respect to the word dog, we see that Ablation Cam highlights the body of the dog, whereas the Grad-CAM does not do a very good job here. Similarly, if we generate visualization with respect to word beach, still Ablation Cam visualizations seem to be more reliable. Okay, so this is one very important property of any visualization, and many people ask me the question like, what about if there is an image with two categories, like there is a cat as well as dog. So we want our visualization to be class selective. It is important that the visualization for one particular object category does not highlight parts of another category. For example, we have an image with two categories, cat as well as dog. Visualization for dog should highlight only parts of the dog in the image, whereas the visualization for cat should only focus on cat regions. And this is the ideal case. Gradient-based methods are pretty class discriminative for most of the times, but when the gradients saturate, the visualizations lose their class selectivity. Here we see an image with two categories, person as well as bicycle. So here is a visualization using Grad-CAM for bicycle class. Due to the gradient saturation, both the person as well as the bicycle regions are emphasized. Whereas Ablation Cam, being gradient free, just focuses on the bicycle region. So if you are trying to plot visualization with respect to one class node, it will only highlight that region for that body of that category. And this is more faithful with respect to model. There was another question like, what are the limitations of Ablation Cam? And so far we are only able to find one limitation, and that is computational efficiency. And Ablation Cam is very inefficient. Since we need to iterate over individual feature maps, it takes a bit longer time than the gradient-based techniques, which only need a single backward pass. And that is an important shortcoming of Ablation Cam. So the takeaway points are Ablation Cam is gradient free and hence does not have a problem of saturating gradients. It performs better on insertion metric. It is class discriminative. It can be used for more involved tasks such as image captioning or visual question answering. It is able to detect multiple occurrences of the same category in the image, and it can also help identify good models from the bad ones. So this is the whole picture. These are the takeaway points for you folks. So I'll like to thank Ravi sir for giving me the opportunity to be part of RBCDSAI and constantly providing me the motivation to do good work. My time at the lab really helped me shape my career towards AI research. I would also like to thank Harish sir for his guidance throughout the Ablation Cam work, even though I wasn't like officially his student. And that's it. Thank you for your time. And I will take all the questions you have now. Okay, so we have with Suyesh Shandhi, yeah, okay. The advantage of Ablation Cam is Yeah, okay. Yeah, so this is something like an area of research, but so the question is like, can we somehow tweak the algorithms to only consider each individual occurrences independently? And if you can do that, you can, the CNNs can be really good at counting images. So inherently, the problem with CNNs is they are not able to count images unless they are given bounding boxes or something like that. And if we are able to do that, yeah, uh, it's difficult task. It's more difficult than you think. I have already thought about how we can do that and tried some experiment, but I just failed. You can definitely take the algorithm and try it yourself, try experiments, but however you like. Any other questions? If you don't have any other questions, I'll just take some questions which were from Harish sir's uh, session. So like Rajan Soni asked, like, what is the difference between interpretability versus explainability? So this is a really good question. So interpretability, when we say interpretability, we are looking at a more on an instance level. So if we change the input, how does the output changes? And what are the reasons for its changes? Whereas in explainability, we are just trying to understand the entire model in whole. Can you explain in a paragraph what the model does? Like if this is this and it will predict this, and if that is that, it will predict that. So something like that. So that's the very subtle difference between interpretability and explainability. It's more of a philosophical thing to differentiate between interpretability and explainability, and they are often used interchangeably. Arun asks, is there a formal definition of interpretability? I think Harish already answered that. So I think I already answered like most of the questions which were there earlier. If anyone has any other questions with related to like Ablation Cam or how it is different for Grad-CAM or any other thing, feel free to ask. I think I have some time. So no questions.
Saurabh, thank you. That was a fantastic presentation, and both Harish and Saurabh. And since others are on mute, so I'll clap for the whole crowd.
Thank you.
And really, that was an enjoyable thing. And for people who are attending, if you want to catch the talk again, it's been recorded. It will be made available on the RBCDSAI YouTube channel very shortly. And we can also share the link with people. And I'm on behalf of Saurabh, I'm actually volunteering him. So if you have further questions, you can feel free to mail to Saurabh. And then just a reminder to close the session. So we have the AI Data Science and AI Summit coming up for the next week. And so soon we'll be opening up a registration link, and we also have details. Please check the website for more information. So, and thank you everyone for being with us today, and I hope that you'll participate in more events and enjoy it. Thank you.
Thank you.